谢乔宇 and Yuping Fang. Thank you.
Opponent. Yeah.
We're team qualified from Conduction to National Technical High School and
Okay. Opponent.
Hello, I am Akash from Typt American School's Senior Donators. This is Justin, this is Eric, this is Guan, and this is Inha.
Then we have a jury member. Let me also introduce National Zhanghua Sifan University, Zheng Zihao, and National Kaohsiung University, Yu Jingzong, and Insignificant, Li Gongxuan, and Insignificant, okay, and Zheng Wenfu. Okay, let's start with the challenge from the opponent.
We would like to challenge the opponent, or the reporter, to number 16 ultrasonic pump.
We reject the challenge.
All right. Now please challenge another problem.
What ones are available? We would like to challenge the reporter to number 4, wind speed.
How many consider?
We accept the challenge.
All right. So, okay, so that's problem number 4. So, please prepare reporter, and in the meantime, please write down the representative name on the record. 12 minutes event.
Thank you. Honorable judges and fellow competitors, my name is Ricky Ho from I-Explorer, Kaohsiung Senior High School. I'm the reporter for problem number 4, wind speed. This is a problem statement that an electric current flows through a coil. When the cold air flows over the coil's temperature will decrease. And investigate how the temperature drop depends on the wind speed and what is the accuracy of the method of measuring the wind speed. So the main focus is the accuracy of the method of measuring wind speed. First, come to my observation, and I do some simple experiment. I heated up a tungsten coil, and when the fan approaches, the wind flows through the coil, and the color will fade, which means the temperature of a tungsten coil has dropped. So then, I do some simple experiment to observe the relations between the resistance and the wind speed. This is the setup, including a hot wire, a fan, constant voltage electricity applier, and an ammeter. And in this video, you can see that when I open the fan, the value of the ammeter has rises, which means that the value of the resistance has dropped. And then I come up with a familiar relations, which is the temperature coefficient. For certain material in certain temperature range, there is a linear relations with the resistance and the temperature. So the hot coil can be a thermometer and a anemometer in my experiment. Then come to my theory, including the heat transfer coefficient, and then I'll introduce the King's law in the engineering area. And the third is the temperature coefficient that I have mentioned. So first, the electricity power dissipated per second will equal to the thermal dissipated every second. And the thermal dissipated will include in 3 ways: convection, radiation, and conduction. The convection is proportional to the difference between the temperature per wire and the ambient temperature. And there is a coefficient called heat transfer coefficient. And then I will introduce it in the later report. So then let's look at the conductions. Because the ratio of conduction is so small in our thermal dissipated, so it will neglect it in our experiment. So then that I have mentioned about the heat transfer coefficient, then how do we combine the wind speed and the heat transfer mechanism together? We have to use the King's law, which is the heat transfer coefficient will equal to constant A plus constant B multiplied by the half power to the wind speed. So then we can transfer our heat transfer mechanism into this formula. This is our final theoretical function. And later, we will use this function to make a graph to under the relationship with the thermal dissipated and the King's law, which is the wind speed relations. So then, in this formula, we can see that there are still some symbols that are not measurable. For example, you can see the temperature of the wire. We cannot use an inverse thermometer to capture the temperature. So how do we measure the temperature of the wire? We can't use the thermometer, so we have to use the relations that I have mentioned, which is the temperature coefficient of the resistance. Yes. And then here comes to my experimentation. First of all, I want to correct the voltage that I measured, because there are 2 ways to measure the resistance. One is for the big resistance and one is for the small resistance. And always we read the resistance by Ohm's law will be smaller than the real resistance. So we have to use this voltage correcting method in our data analysis. And the experiment 2 is I want to measure the temperature coefficient of every materials I use in a later experiment. And the setup is including the heat supply, the milliometer, and hot wire, and a thermometer. And this experiment depends on this theory. So finally, we come come to the experiment 3, the wind speed, the relations between the wind speed and the heat transfer. This is a setup, a DC electricity supply, a hot coil with different materials, and a fan, anemometer, thermometer, and in the box are the ammeter, voltmeter to measure the resistance. And this depends on these relations that I have mentioned. So then, I will discuss my experiment results, including 3 parts, different materials, and radius of the enameled wire. Third is the radius of the coil. First, materials. And I have used 2 different materials. One is the nichrome and another is the enameled wire. And this is their temperature coefficient, which is the slope in this graph. And these 2 graphs you can see by the correlation coefficient. You can see that the enameled wire has a better fitting curve. So then in the later experiment, we will use the enameled wire as a better materials. The next discussion is the radius of the wire. So I use the different radius, which is 0.23 millimeter and 0.35 millimeters, and their lengths are all the same. So this is a result, and the third is the radius of the coil. So this is the four different radius of. This is a result for the 4 different radius of the coil, which is 1 times, 1.2 times, and 1.5 times, and 1.8 times. And from this 4 graphs, you can see a specific phenomena. In a high wind speed, you can see that these 4 dots are higher than the theoretical model. So then, how do we solve this problem? That we have to use a correcting method. Is that I have to do the arrow, just the theory, the theory minus the actual mod over theory. Then we will have the enroll, and we have relations between the times and the enroll, and we can use this correcting method to correct our data. So then we can see that after correcting, we can just pull the dot onto the fitting curve. So then here comes to the key point, the accuracy of measuring the wind speed. So this is my setup. It has same as the experiment 3, but there's still some difference. Is that in this experiment we rely on the anemometer and thermometer to measure the temperature and wind speed. But in our structure, we have to measure these 2 things independent. So we have to use 2 wires. Then we have 2 functions, and we can solve 2 variables, which is the temperature of fluid and the wind speed. Yeah. So you can see there are 2 wires it is used in my structures. And this is the result. For example, the theory is what I calculate, and the actual is the actual wind speed I measured. So this is the percentage of enroll is how I to express my accuracy. And I have to do 10 times of the experiment, and this is the average percentage of enroll. The accuracy is that when measuring wind speed is 8.666%, and the temperature of the fluid is 1.45%. So it is accurate because the commercial hot wire anemometer is about 5% of enroll. So then the next question is that we have a high accurate, then do our hot wire anemometer has the time accuracy? Because when we have to measure the wind speed, we have to wait for the thermodynamic equilibrium point. Then there will have a long reaction time. And I use Arduino to measure the time vs the time and the voltage. So when the voltage is a constant during time, then it is called a thermodynamic equilibrium point. So this is my result. When the wind speed is 1.8 1.8 meters per second. The reaction time is 31 seconds, and the wind speed is 3.8 millimeters per second. Reaction time is 26 seconds. Then we will get the conclusion that when the higher wind speed, then we will have a lower reaction time. The conclusions for my report. I have to do the parameter for first the materials that we have get the conclusion. Enamel wire is a better material and it will not oxidize in the air. Second is the radius and the radius of the wire and the radius of the coil. So I have to do some corrective methods when the wind speed is higher, then I can get a more accurate value. The second is the corrective method I use in my experiment, the voltmeter correcting and a relations between the in-roll and the radius of the coil. And this is my report. Thanks for your attention.
Next questions.
First of all, please answer yes or no. First of all, did you consider the turbulence of the wind that caused by the plant?
Turbulent?
Yes, the eddy flow. Did you consider anything about it?
You mean that like I just calculate the Reynolds number and say it is turbulent or not?
So you didn't show the presentation, right?
Yes, I
Okay,
can
okay.
show it.
Next question is, did you assume that the wind speed will be uniform when you use the fan? Because if the difference is, yeah, just this.
No, I have to do the experiment as well.
Can you answer yes or no?
Just I put in the thermometer and in front of the fan, and just when the fan
So there's a distance between the fan and the coil, right? There's some distance between the fan and the coil wire.
Yes, there is a distance, but I have to do some corrective method, and I can tell you what I have done in later discussions.
Okay. Next question is, do you have any numerical data to argue that the radiation is insignificant, and you are not even mentioned about the conduction is negligible? Do you have any numerical value to prove it?
Yes, there, please. Yes, I can show you the ratio, please. Yes, I will show you later
So yeah,
discussions.
since you said yes, I'll just skip the question. So next question is, did you measure the circumference of the wind air fluid volume that passed the whole wire?
Can you say again?
Did you measure the circumference of the wind air fluid
What's
volume?
circumference?
Let's say this is coil, and the circumference is the parameter of the.
Okay, time's up. Okay.
I did a video of my presentation, on my presentation, because like, I don't know, it's difficult because like, I feel like the TV, I don't have any actual video presentation. I have like an example of
can take the stage. 4 minutes.
Hello everyone, I'm Hyunwoo Chun, and I'm from the team Lowrider. Today I'm going to talk about the opposing for the wind speed that this reporter talks about. So, as my aspect, I will approach the, since the problem statement wants to talk about the accuracy of this method and investigate how the temperature drops depending on the wind speed, I'll try to approach this topic with the 4 steps. First, I'll think about how the heated coil is cooled. Second, I'll try to investigate the relationship between cooling and the velocity of the wind. And then I move on to talk and investigate about the relevant parameter that affect cooling. And then in the end, I'll approach this topic by comparing the accuracy with the analysis about it. So overall, the reporter did a really good job. She considered the convention, radiation, and multiple independent variables with the parameter. She also did a good job for strong equation back up the theory and also clear demonstration of the phenomenon. However, she didn't mention about the turbulence, and also she didn't calculate the, she will provide the calculated number, Reynolds number later. Also, she didn't explain causes of the experimental error, which is such as thickness of the wire, and also she didn't modify theory to correct her errors instead of creating fitting lines on the graph. She neglected conduction without proving that it's negligible with numerical numbers, and also she didn't consider about the orientation of the wind, that the wind can be shooted in the perpendicular but also parallel. She didn't mention about create the formula of the accuracy for the system instead of just explaining a general trend. And also there's some issues in the experimental setup as well, such as the wind is keep dispersing, not just going into it. But there's some problem that she didn't assume that the wind speed is uniform. Because of the fan, there's some further issue that the wind can be dispersed to the coil. So overall, for this upcoming 10-minute discussion, I want to talk about a basic phenomenon, which is the radiation and conduction insignificant proof at actual numerical value. And also I want to talk about the theory's measure of the accuracy and then comparison of the accuracy measurement between the same independent variables. I also want to talk about the relative vector that touch the wire, thickness of the wire, orientation of the wind speed. And also, after looking at their experimental and setup, I want to talk about the wind from the fan is dispersed, the issue about the funneling issue, and also I want to talk about the measurement of temperature, equipment, and correlation of wind speed and voltage temperature. So I'll jump into the discussion with the reporter. So sorry about the lack of explanation about the circumference. So what I mean about the circumference is the circumference of the moving air that So here are wires, it's like this, right? And airs coming, let's say, going into the paste. And what I mean about circumference is these
area.
Yeah, area of the fluid volume that can actually impact into the coil wire. Yeah. So did you define anything about the circumference, or did you have any range for the circumference that actually impact the cooling of the wire?
As you can see in my setup,
Yes.
my trim was yes, my trim was like this. And you can see that
Yeah.
I have said that my radius of the wire is 0.23 millimeters, and I can use this to calculate the areas.
So you're saying, what is this number coming from? 0.23 millimeter?
It's the radius of the wire,
Yeah.
or the enamel wire.
But what I mean is, so I think I destroyed the coil that you set up. Let's say this is the coil that you're using. I want the circumference of this range of the air fluid that can actually influence the coil of the wire. That the fluid of the air that can cool down the coil wire.
Yes, because my
But
trim.
how can you use this number to find this range of the fluid volume that can influence to the wire?
No, just we mean that when the wind is when the fan approaches,
Yes.
then the wind will flow through the cooling patch.
Yes.
So because my turn was so the width was so
Small,
large.
large.
So the wind can just happen through it. So you can just calculate the areas.
So you're saying that if an area in the really far away can affect the cooling of the wire, coiled wire.
No, just
So you don't have any range about this. Can you set up any range that the wind caused from the fan that can actually cooling the coiled wire? Do you have any range to see?
just mean that how far the wind speed can influence it.
I meant that you in your model, your equation doesn't contain that what is the range of the air fluid around there can actually cooling this wire.
Because my in my theory is that
Yes, sir.
if the coil is here and the fan is here, then the most thermal dissipation caused by the wind speed, and also the wind speed will dissipate or decrease by the distance. And will decrease by distance like this. So when the fan is far and far, so the wind will be too small that can be neglected.
Okay, so
Yes.
you're moving the fan farther from the coil sometimes, right?
No,
So you're-
just I have just you can see my structure says, and every time the fan was at the same positions and the wire at the same positions. So every time I measure was at same positions.
Okay.
So I have measured the same wind speed. So I think you mean is that the measure the area that
Yeah.
the wind can achieve.
Actually influencing the coil.
Yes, but I in my experience, I have just control the conditions that there's no other wind speed produced from the environment.
Yeah, so I want to talk about that point because
Yes.
let's say this is your coil and you blow a fan from here, right?
Yes.
Then when the fan blew off, this fan, we can't guarantee that all of the wind is uniformly going inward because there's some funnel issues. Because the wind of the wind caused by the fan is dispersing outwardly, so you can guarantee that there's a uniform wind fluxing into the coil. However, you didn't assume that there's the uniform wind of the coil that you're measuring.
Just the most thermal dissipation is caused by the wind speed.
Yes.
So in my theory, I can assume that the only origin of the wind speed is by this fan.
Okay.
Yes.
Yes, but I want to say that let's say I think I too exaggerate the diagram, so let's draw like this. I'm not sure. This is
But in this problem statement, we're talking about how to make our structure more accurate. So we
Yes.
have to. So you can see the commercial hot wire anemometer it has a very small wire, right?
Okay.
So the smaller wires it may be more accurate. So if
how can you say that the small coil wire is more accurate than
because the range is smaller, then
radius of the
the range is smaller,
Okay.
so there will not be another this.
okay. Yeah, and I think that you're going to show me the numerical proof of the radiation and the conduction
Yes,
is
and I can show you. Please. And I have calculated it is a conduction, radiation, and conduction. You can see that the conduction is so small that that can be neglected.
Then I have a question for the slide because you only in the presentation you only cross out the conduction, not the radiation.
Yes, because I
Is there any reason that you say the radiation, although it's really small as you can see in the number?
Yes, because the conduction that I can calculate before fitting, that the K and L and AC is constant.
Okay.
So and the radiation that we didn't know the emission and we have.
Okay, got it.
Yes.
Now I want to move to the next question because you use the thermometer, right? Let's say there's a thermometer that you're using the temperature. Because I think you're not using all of your surface to measure the temperature. So let's say this part you're measuring the coil temperature, but this one, they're capturing the environmental
The way
temperature.
I measure the temperature of the wire is using the temperature coefficient.
Okay.
Yes.
So,
you
but
can just
didn't you
see
mention
my.
that you use the thermometer?
Yes, thermometer is to measure the temperature of the food, and it is built in this anemometer.
Okay.
Yes.
Yeah, okay. I want to move on to the next point. I think that's enough for the answer. So you mentioned that the higher wind speed can lead to the lower reaction time in the conclusion, right?
Yeah.
But you didn't prove any reason that why the higher wind speed that led to the lower reaction time. So do you have any explanation that why that caused the slower reaction time? It's in the conclusion. Yeah.
Yes, but it was related to the fluid dynamic that
Yes.
I cannot explain, but it was just a phenomenon that I have observed, and I have responsible to tell them that in my structure, when the wind speed is higher, I have a lower reaction time.
Okay.
Yes.
So I think I want to add on that point because next time you can calculate the turbulence because when the wind speed is really fast, there's some turbulence that actually impact the coil of the wire cooling. So I think next time you trying to measure the eddies for that part, then it will be more clear correlation between. And also I want to go over that your correcting method is just fitting the line, not actually you're just fitting the graph to the correct to make accuracy. So I want to is there any equation that prove your accuracy, or how does the fitting line can prove that your experiment is accurate?
I can slowly explain that when the coils is like this, right?
Yep.
And there is also some head that store in the coil, right? So when the wind speed is larger, then the heat will maybe just blow away.
Okay.
So then you can see in this graph. So when the aperture is larger, then the more heat it will dissipate. So this is why when in high wind speed it will have difference with a lower speed.
Yes, so that's I think that's related to turbulence, but you didn't any.
This is not really related.
So you're saying that although there's high speed, but there's no turbulence at all.
Then how do you then? So maybe just I want to tell this is
Yeah.
that I found a way to correcting I found a correcting method to correct the wind speed
Okay, yeah, that
for
makes
my
sense.
structures.
Yeah.
So it will have a higher if I do this correcting method, then they will have a higher accuracy.
And last one,
And then I want to ask a question is that can you define the turbulence?
turbulence is the eddy floor that there's a wind. If let's say there's a really fast wind speed,
Yes.
then it can actually disturb the other fluid mechanics that flow into the.
Yes, but I remember that the King's law I used
Yeah.
was also that calculated by the Reynolds number,
Okay.
and Reynolds number was a coefficient that can define the turbulence,
Yes. So
right?
do you have any number for that coefficient?
No, I
Because
don't know
that
how.
Yeah.
I
Because
don't
the
know.
coefficient can prove that the wind is turbulence or not. So do you have any number that actually prove that there's no turbulence?
I cannot prove that there's no turbulence, but as I said, when I put an anemometer in front of my fan, and the value of the anemometer was a constant, and then maybe I can just prove that there is not a turbulence.
So you're
Time's
proving
up.
without.
Because
Time's up. Yeah, opponent
Thank you.
will summarize.
So just now we discussed about between the direction of the wind speed blowing from the fan into the coil, and we talk about the coil size and the wind direction. We also talk about the thermometer placement and application that recorder used temperature coefficient. We also talk about the area of the surrounding the coil, that the surrounding airflow and its impact that we talk about. We further the discussion to talk about the Reynolds numbers and also the turbulence. We also talk about the fan's lack of furling the wind to the coil wire, and also we talk about effect of the wind direction and turbulence. And then in the last, we defined the turbulence and the finding Reynolds number that the reporter doesn't have any number to prove that there's no turbulence. Thank you.
Reviewer, please.
Okay, so I have some questions for both sides. How do you think, because we're talking about accuracy right here, right?
Yes.
So I want to know about how to define accuracy. How much do you think it's accurate enough? Like just a brief answer. Like maybe how many percent for both of you?
I'll use the slope error to find the accuracy for the wind speed and the temperature relationship.
Okay, then what about you?
You see in my report, I use the percentage error to define my accuracy. And in this graph, you can see there are different definition of the accuracy and precisions.
Yeah, okay. Then I also want to ask, because you guys seems to have a different idea on how if the radiation and conduction can be ignored or not. So I want to so I'm asking the previous question because so do you now still think that can you tell me how well
You can see in this graph, this is the ratio of the convection, radiation, conduction in the thermal dissipator. And you can see the value of conduction is really small than the convection.
Yeah, I know it's really small, but we're talking about accuracy right here. Do you think this one maybe it will change? Like 0.1%, will it really change? Will it really change your definition of accuracy? And what do you think about that?
So you're saying that the small accuracy error can not prove the accuracy, is what you mean?
No, I'm saying that because we're talking about accuracy right here, so we need to know how do you define accuracy? How small of accurate do you think it's accurate enough? That's it.
So in that case, we need to prove before starting the experiment. So we need to set some percentage, like 5 or 10%, that if you exceed this number, it's going to be the error, or if it's going to be below, then it's not going to be the error. And then I'll do the experiment and then find and compare it with the number that I defined before the experiment.
You can see that this is much larger than 1%, so it may be neglected. And also maybe I can do the graph with that if I just count this three ways into the graph and not count these conductions. And maybe you can see that there's no difference between if I neglect conduction or not.
So both of you are talking. So you guys were discussing about how the turbulence will affect. So in your imagination, how much of the accuracy will the turbulence affect?
I think it's based on the wind speed, because unless the wind speed is slow, then there's less likely there's a turbulence that influences the coil. But when the wind speed is increasing, and there's a turbulence that actually disturbs the cooling the wire from the omit-heating.
And that I have mentioned the King's law, this functioning and engineering, and this A and B is also will be calculated by the Reynolds number. So in my opinion, the effect of turbulence will also including in this King's law. So yes. Thank you.
to, I think for the problem introduction, we just have to clear up that the most important part of the, of
The projector.
Projector is not on. We have a lot, but the projector. Yeah, okay, thanks.
So I just think we have to clear up that the most important question that we're talking about right here is the accuracy. Okay, so let's summarize up the reporter's part first. So they had clear observation video, and they had and their setup was pretty much all that, and then they also have a lot of meters to calculate and to get many of their constants, and also for their theory they used all of these, but they ignored conduction and in their experiment they have very clear images of different setups, and they have 3 parameters considered, and I think that's pretty much enough. But I also think that they could I expect from more parameters of like maybe environmental parameters to be considered. And then in their conclusions, their deviations are well considered, and they even made a correction equation. However, I think their correction equation lack a physical explanation of why and how did they get this correction. So points from the reporter. She did a good job reporting, and she gave really clear speaking, and they have a clear data and a clear theory, and then they found out the deviations and correct them with when it does not match with the theory. They only consider a few different situations in different parameters. Like they only measure two of them in every parameters, and I think maybe more should be considered. Okay, and then points from the opponent. He gave really specific questions, and then he even gave some practical suggestions to make the theory, to make the experiment better. And however, I think he should make give more specific when they're methods when they're trying to lower the deviation. Like how are you going to lower the deviations in your opinion? And then also, so one clash part was how much the wind could actually be captured. So these are how they thought, and we partially agree with the opponent, but we also suggest that there can be also a sensor, or maybe the other side of the coil to measure and calculate to eliminate the deviation. And also we also have the reaction time. We don't have a really clear physical explanation why we get that, but I understand that this is an observation that the reporter saw. And then next one, so we already discussed about the conduction and the radiation part, and we think that after you define the accuracy, how much do you think is accurate enough, then we can also maybe eliminate or keep them. And then we also discussed all these, and then some missed points was I hope to ask that the reporter could more explain on when the correction equation should be used, because they didn't really give an explanation of when are they using this, or they're just saying high speed, but they're just saying high speed, but not exactly how high enough. And I think that's really important because you're giving a correcting thing. So yeah, and then you're also I hope the reporter the opponent didn't ask about how did they get the correction equation. Thank you.
Reporter, please conclude.
Thank you. Honorable Judge Bao Delegates and the reporter. And now is my concluding remark. And the coil thermal dissipated is considered in a function. The electrically dissipated will equal to the convection plus radiation, and conduction can be neglected in our experiment, because the ratio of conduction that I have calculated is 0.0018%. It's so small that can be neglected. And the way I measure the temperature and the wind speed is by using the temperature coefficient. And I'm using the King's law, that the King's law is just calculated by those fluid dynamic coefficient. So in this King's law, the effect of turbulence can be included. And the third is that my own contribution in this experiment is that I create an independent wind speed anemometer, because I use two wires that I can measure the temperature of fluid and the wind speed at the same time, and also that I have my device is with a high accuracy. So this is my concluding remark. Thanks for listening.
Now is time for the questions from the jury. So any questions from the jury? Then you don't. Then I have some questions. I think the problem says how the temperature drop depends on the temperature. That's the whole issue of the problem. And also the accuracy of the method, right? So I'd like to ask, how accurate is the King's law you are trying to use? So that's you basically assume the King's law from the beginning, right? But actually, I think the problem, that's the purpose of the problem, to ask you to investigate it.
Because I have considered a reference in Cambridge, and as for engineering, and all the commercial anemometer is using the King's law. And in my opinion, it is I cannot understand the meanings of those fluid dynamic, the coefficient in the fluid dynamic. So I choose to use the King's law because it is more, for me, it is more easy to understand it.
What about opponents, your opinion?
I'm not sure about we need to use the King's law, because what I think was when the wind's linking to the coil wire, we also need to capture the velocity of the wind flowing to the velocity and the volume of the wind, like part that actually going into the wire and then connect to the wire to cooling down the ohmic heating. So I'm questionable about the King's law, although King's law is like worldwidely proven, like really credible laws. So I'm not sure that it's credible to use it and assume that all of this situation is based on the King's law.
Then why did you keep asking this turbulence?
Turbulence, because I think that there's some threshold that when the wind speed became faster, then there's a turbulence that can block, like disturb the fan, like cooled fan, a cooled air volume that can cooling down the coil.
Okay.
So I think that turbulence disrupt those cooling motion.
Right.
Yeah.
How about your?
Okay, so I think it's pretty close that she used the King's law, and I think if there's references, then it's I think it's reasonable to use it. But however, we don't really know that how under what conditions can the King's law be put in, like how idealistic, how the environment will affect it. So I think that's also variables for us to add into the King's law in order to make it more accurate.
Okay. Any more questions?
So I would like to ask the reporter. So could you go to the slide which you list the dissipation, heat dissipation from various channels?
Or the ratio.
Number.
This one?
Yes. And so you choose to neglect the heat loss from conduction. Why don't you neglect the heat loss from radiation based on your estimation?
Yes, before fitting the theoretical line, that I didn't know the emission coefficient. So if I assume the emission coefficient is 1, is the largest number of the emission coefficient, then the effect of the radiation is so big that can be negative. So I choose to retain it. But before fitting, that I can just calculate the effect of the conductions. Yes.
So you are thinking that the emission coefficient is that low?
Yes, and just after fitting, you can see in my I have to do the relations between the heat transfer and wind speed, and just during this fitting, I just put it in the decimals, and I can just calculate the emission coefficient. Yes.
Any more questions?
Okay, I will follow on your question of the reporter. can you tell me if now I know the temperature drop, like maybe 3 degrees Celsius per minute. So can you tell me what is the wind speed
3 degrees Celsius, then
per
I
minute
can,
drop with the temperature drop?
temperature, no, I cannot tell you, but, cause I have to use two function that, the two function, and then I can have two variables. Just like, I have two words, and I can get two function. I can calculate what's the h by the heat transfer mechanism, and then I have the two function for this equals to the King's law, and this, and in this would have a variable called temperature of food, and we have two variables, so by this two function, we can get these two variables, and yes. So we cannot just using the temperature drops to calculate the wind speed.
Okay. All right, so I think time's up. So let's just do the grading. Okay. So for the reporter, please keep the grading. Right. 5, 6, 7, 6, 6, 7. For the opponent, this video grading. 7, 5, 8, 6, 6, 7. For the viewer, 6, 6, 7, 6, 6, 8. Right, so any comment do we want to make? I just want to make a comment. As I said, the whole problem should try to find the relation between the temperature drop and the current velocity first, instead of starting from the King's law for fitting. Right, so that should be the spirit of this problem. Actually, the King's fitting, the exponent may not be 1/2, 0.5. So you are treating that as a fixed number, so probably that's one of the sources for the error one. Right, so that's my comment. More comment? Okay, if there's no comment, so we finish this set. Okay, let's take a break.
Fluid dynamics. We'd like to reject number 70 then.
Team H105 would like to challenge the question number 2, circling magnet.
We would like to accept number 2, circling magnet.
Please write down the representative of each team. Reporter, you have 5 minutes to prepare.
看得见吗？这看得见。
Reporter, please present.
Hello, I am Akash from the Non-Editors Typt American School, and I'm going to be presenting number 2, circling magnets. So the problem statement is that button magnets with different diameters are attached to each end of a cylindrical battery. When placed on a sheet of aluminum foil, the object starts to circle. Investigate the motion, how the motion depends on relevant parameters. The focuses of the project in our experiment were that we need to explain why the circling phenomenon occurs in the first place, and examine its underlying principles. And then we also need to model and observe how different parameters change the circling behavior. So I'm going to do phenomenon investigation, and then we are going to just look at a theoretical model for the phenomenon. We're going to look at experimentation and discussion, and then I'm going to conclude my presentation. So for phenomenon investigation, the way we arranged it was we had a battery and two basically cylindrical magnets on either side of the battery, and we didn't use glue to connect it simply because the battery is magnetized by the magnets. They stick together, and so they don't actually slip. And so if you see here, we always put the north pole on the outside and the south pole on the inside for a reason we'll later explain. And so here's the side view, and then here's the top view. And so essentially, if we look at this, there's going to be a current through the magnets and the aluminum foil are all conductors. So there's going to be a current through this loop, and that's going to create a current upwards on one side and downwards on the other side. And of course, because the north is on the outside for both of them, if we use the right-hand rule, we can see that for the side over here, the magnetic field is in this direction, and the current is downwards. So there's going to be force outwards towards the viewer. And on this side, the current is going to be upwards, and the magnetic field is in this direction. So there's going to be a force outwards on this side too. So basically, there's going to be a force because of the interaction between the magnetic field and the current on both of these magnets, which will cause it to move forward in this way. And because one of the magnets is smaller than the other, for it to move, for it to roll, it has to move in a circle instead of just in a straight line because the sliding friction is much greater than the rolling friction. So here you can see the phenomenon, and it moves in basically a perfect circle here. Next slide. So for our theoretical model, basically the current, as we showed before, combined with the magnetic field, using the right-hand rule, we can see provides a force in one direction, which ends up being a torque on the body. And this constant torque and the rigid connection between the magnets and the battery causes it to move in basically a perfect circle around the center point. And the main factor that opposes the motion of the magnets, because there's the magnetic force, what opposes that is the rolling friction on the edge of the magnets. And so we assume that there's no slipping of the magnets on the surface, because essentially we obviously observed that it was rolling, and the roll of this sliding friction is greater than the roll friction by enough that essentially there's no reason why it would be sliding. Also, the rolling friction we assume was dependent on the velocity, the contact area of the magnets, and the aluminum foil, and the radius. And I want to note now that essentially there's friction between it because although it's tilted, the aluminum foil can be indented slightly. So that creates area of contact between the magnet and the aluminum foil. So if we see here, as I explained before, the green represents the magnetic field, and that's coming outwards on each side. And then we use the right-hand rule to see that when the magnetic field is coming outward and the current is going either upwards or downwards, there's going to be a force in one direction. And because these are on opposite sides, the forces will go in the same direction. And I want to note now that if we were to switch the north and south poles, that would make it so that essentially the forces would go in opposite directions, so it would have to spin like a very, very small circle. And so that's why we instead use make both poles on the outside be north. And then here's our equation for torque. So for the inner magnet, we just use the basic torque or force equation, IR times the magnetic field, and we combine these here. The radius over 2 is going to be times the force is going to be the torque for each of them. And so if we combine that, we can get this equation where the torque is equal to the current times the radius squared over 2 of times the magnetic field for each of those separate magnets. And then, so if we want to use the torque to find the angular acceleration, how it accelerates over time. And so for the we show what it's going to be here for the current in each of them. And so the angular acceleration is going to be the torque over the current. So we sum all of these values here and put that in the denominator, and then we use the slide we had in the last slide here. Sorry, I said current here. I meant the moment of inertia. My bad. I spoke. So here, this is current, here, this is moment of inertia. The numerator is the torque that we showed in the last slide, and the denominator is the moment of inertia, which we summed for the inner and outer magnets in the battery. And also we need to account for rolling friction, because rolling friction is the force that's torque that's opposing the motion, and so that can be calculated by the force of the friction would be negative CA, where C is a constant, A is the area, negative CA V, and we split the velocity into the angular velocity, which is omega, and r, and then to turn the force into torque, we also multiply that by r again. That's why it's r squared. And so to get the net angular acceleration, we subtracted the torque from rolling friction in the numerator. And then, so here's the governing equation. Here we have the R2 is the radius of the large magnet, R1 is the radius of the small magnet, and then here are the different distances. And we used the radiuses of the magnets to find the length from the outer magnet to the inner magnet here, and the length from the inner magnet to the center of the circle. And that leads us to this governing equation here, where this is the angular acceleration. And so, yeah, once again, the constants here that change are L is the length of the magnets plus batteries altogether. And then R1, R2, and RB are the radii of the inner magnet, outer magnet, and battery. The M's are all masses, I is the current with the one with the arrow, and then C is just a fitting constant for the rolling friction. We'll explain how we found that later. And then B for both of those are the magnetic strengths of each of the magnets. A is the contact area. We'll explain more about that later, how we estimated that. And then omega is the average angular velocity. So here, this displays the information for each of the different magnets and the battery. So the radius is just the radius, The magnetic field we only show for the magnets because the battery, of course, has no magnetic field. And then the mass is for each of those. And so the reason why this doesn't have a magnetic field is that's just the battery. All the blue ones are different magnets that we tested. And so, so here we can show the experimental setup. That's just a single layer of aluminum foil with the battery on top, and then we used tracker to track the radius as it goes along the circle. So when we did different tests, the independent variables were the combinations of different magnets that we put together, and the strength of the batteries and voltage and the number of batteries. We put them end to end. And then the dependent variable was the angular acceleration, which we showed the equation for before. And the control variables were aluminum foil. We always had one sheet of aluminum foil, and the type of battery used. So to determine the constant C, we essentially put the same two magnets on the outside, so they would roll in a straight line, and we tracked that motion and fit it so that we could find the constant C. It's equal to 0.387. And for A, that's the area of contact between the magnets and the aluminum foil. And basically, each of the magnets is going to be tilted because it's not completely flat and it's going in a circle. It's going to be tilted, and the aluminum foil, as we see in the grooves, can be indented slightly. So we essentially saw that when it was going in grooves that had already been created, we measured it to be that the area was approximately 2/3 of the length of the bottom of the magnet, and when it was going on a new track that had no grooves, it was only 1/2. And so here is our data. We found that for these are the blue is experimental, red is theoretical. We used 3 different inner magnets. The outer magnet was stayed the same each time. And so here you can see the comparison between experimental and theoretical. They're all very close. Next. And so for the number of batteries, we can see how we just used a different, this was a different number of, these were the different outer magnets, sorry, and once again, once again, this is number of batteries, so once again, the blue is experimental and red is theoretical, and when we add more batteries, we can see that the overall angular acceleration decreases. We presume that this is because of the added weight of all the batteries. And so with battery voltage, we found that over time, this is a short circuit that we're doing, because the current can go straight through, there's no resistance really, or very small resistance. So this will go through the battery's voltage extremely quickly. So we can see just over the time of seconds how the voltage of the battery decreases, and therefore the angular acceleration also decreases with that. And wait, can you go back real quick? We found that because all of these can be seen to be proportional, the angular acceleration and the voltage and current, because the resistance stays constant. So as you saw, there was some error between experimental and theoretical bars. We thought that this was because of the induced magnetic force could lead to a slight overestimation of the angular acceleration. That's for the ones where the theoretical line overestimated. For the ones where the theoretical bar actually underestimated it, we thought that because the magnet's going to be slightly off center, it could really lead to slightly reduced angular acceleration. So, in conclusion, we found the following governing equation for the angular acceleration by taking the current, magnetic field, and rolling friction into account. And so we found that the radius, moment of inertia, and current and voltage all have a significant impact on motion, and as you can see, we all took those all into account. And the impact of the moment of inertia appears to be more significant than that of the magnetic field and current, and the error source can be found to be because of the induced magnetic field and non-centered magnets. Thank you.
Opponent, please ask the question.
Please give me the brief answer, yes or no. Do you think the output of the voltage of the battery is stable?
The amplitude?
The output of the voltage?
No, as I showed before, the voltage runs through pretty quickly, so it decreases over time quite quickly.
Thank you. Okay. And do you think the internal resistance is negligible?
The internal resistance
Of the battery?
Of the battery?
Yeah.
We found the, can you go back to? We found the current and voltage for each of those, so that already takes into account the resistance, so we didn't have the resistance in our equation because we found the voltage and current, so we don't really need to find the resistance because if you just use Ohm's law.
And I have seen that the experimental result of your graph is just a number, not don't have any deviation on it. So
What do you mean deviation? This is the error represented here between the experimental and theoretical bars.
okay. So you compare about the reality and the theory, which is the left wheel and right wheel is slightly tilted, right?
Yeah, so we tried to put them on the battery as close as we could to the center, but because it wasn't perfect, the slight off-centeredness could cause slight error, and that's what we think will cause the error.
And please turn to page 10. The rotating inertia, you just simulate the magnet into the symmetrical form, right?
Yes, our magnetic force cylindrical.
Okay, thank you.
Opponent, you have 2 minutes to prepare.
先看哪画面？这画面是哪个？他现在是哪个？现在用这个。对。这个画面对。来说说看。以往超级病。
Thanks for the excellent presentation of the reporter. Now I will start my proposal. And I think I don't need to read the problem again. The advantage of their setup is include both clear picture and photo, which is easy to read. But there are no observation to see the actual movement. And their theory is clear about on assumption. But there are lack of data number. And their conclusion advantage is that to let us acknowledge the way to improve. However, there is no clear physical explanation equations. So your strong point is that the present with fair and helpful hand gestures like the right hand laws and clear explanation of the whole experiment process. But there are some suggestions we have to give you is that you didn't consider much deviation in environment and how much the data is in your experimental results. And I think I can skip to the discussion part. Okay, can you please turn to page 20? Can you please explain why alpha is the relation between the alpha and t is like that?
That's just what we found on our theoretical. That's what we found on our theoretical curve, and essentially our the data we found through experimentation fit that exactly.
So there are no mathematical equation to prove the alpha is the relation between alpha and t.
What are you trying to find?
I was trying to find the mathematical proof of the alpha and t relation.
What we were showing is it's linearly there's a linear relation. That's what the graph was showing. Is that we found that there's a linear relationship between those two.
Okay, thank you.
And the theory supports that.
And I still think the resistance of the internal resistance of the battery is an important thing to consider. Because the internal resistance will increase slightly when the quantity of electricity is become lower.
Okay, so because we calculated, we found the voltage and current of each of these for each of the different numbers of batteries. I mislabeled that earlier. We could just find the resistance, and that includes the internal resistance of the battery. So I think that's what you're trying to find. So those are for each of the three trials the resistance nodes.
Okay, thank you. And please turn to the observation part, please. Video. if the magnet is rotating faster, do you think the friction is great enough to support the force to not let him go horizontal direction?
Can you,
Like, this is a root of the devices, right?
this is over, okay.
Yeah. Okay. And this is our devices. And you will go like this one. And if the velocity is too big and the friction is not enough to support the motivation, you will go like horizontal directional motivation, right? So do you consider about the this?
Yes, so basically you're saying that if the velocity is high enough, then it will overpower the sliding friction and it will move out.
Yeah.
So we did many trials with many different parameters, and we found that in none of those did it move out of the circular arc that we tracked, because the sliding friction between the magnets and the tin foil is enough to, the aluminum foil is enough to make it so that it's not going to it's not going to go outwards before the basically the force of the magnetic force is going to be matched by the sliding or the rolling friction.
So do you have any graph or picture or even the video to prove this?
We have no videos of it going outside of the circle because it never happened.
Okay. So let's back to the forward question. So how many times do you do the experiment? Because I have saw that your experimental error is quite big.
Yeah, so it's so we do each of these once, and we explain the theory by talking about how there might be it might be slightly off center, but in addition to that, can you go to the slide that talks about error? Here, so basically, there's if the magnets are slightly off center, it can lead to the error, and especially in the ones where the angular acceleration is very small, such mismatching can lead to a higher error. In addition to that, there may be an eddy current that opposes the magnetic force and goes in the opposite direction, which can lead to overestimation of the theory.
Okay. And I want to know another thing is that the result of your acceleration of the angular acceleration is a number, right?
The angular acceleration, yeah.
But the angular acceleration and the time function is not the straight line, because of the resistance.
Yeah, the angular acceleration is not going to start at 0. It's going to decay over time because of the friction. So it's going to start high and then go down to lower because of the friction.
Oh, correct. And so do you consider the curve radius of this curve?
To the curve.
I mean, if this is a curve and it has a rotate sensor and the R, I think this R.
This R is this supposed to be the path of the
Path of no function of the.
So what is this point?
Just to describe the curve of the function. This
So
function.
we're finding the rate.
Yeah.
What we showed is the angular acceleration of the star, So what we're showing each of those graphs is, or each of the bar graphs, is angular acceleration initially.
So I have seen you have do the north and south, like the set of this, right?
Yes.
And,
No. These are switched. The north is always on the outside.
I know, but if the set is like this, the rotating radius will be clear to observation, right? Observate.
We use the one on the top, yeah.
Yeah.
We can observe it.
So why don't you use this one?
Oh, okay, I explained it at the start earlier. So basically, if they're in opposing directions,
Yeah.
and when we use the right hand rule when they're both on the outside, can you go back to the start where I showed that?
I know.
So
That-
basically,
Oh.
and so using right hand rule, we can see that the force is both in the same direction.
Yeah.
And so when we tried switching it, essentially the force is going to be in the opposite direction, right? So and it ends up being here. We use this. The force on one of the magnets is going to be forward, on the other one is going to be backwards.
Yeah.
And essentially that means that instead of rolling in a circle, it would have to instead slide in a very, very small radius circle. And it can't. When we did this, it never overpowered the sliding friction, so it never, when we aligned it this way, it would never move because it would just, it would be sliding. It wouldn't actually be rolling, it would just be sliding. Yeah.
Okay. When the device is rotating, circulating, do you analyze the different friction of the two wheels? Because they have different friction to produce the different torque.
We found that basically there should be about the same area of each of them touching the actual touching the foil. So basically we can just sum the area, and the area estimation accounts for both of those together because they should be approximately the same.
But the area will not impact the force
The friction?
of
It
the
does.
friction. Yeah.
The area is part of the friction. Oh, wait. So you're saying we should have accounted. What do you think we should have done?
Because the friction is equals to mass times gravity times the coefficient, right? So there's no area in this version. So why did you think the area is?
Oh, in our calculation for rolling friction, we had to include that because the area will change depending on whether or not it's in the groove or whether or not it's in the groove of that was already presented. Because when it starts circles multiple times, it creates a groove in the coil. So we had to find a way of accounting for whether or not it's actually in a groove, and so we used area for that.
Okay, so do you think the shape of the magnet is cylindrical, right?
Yes, we use cylindrical magnets.
So does the thickness of the magnet affect the because it affects the mass of the center, which in the position, right?
Yes. So I mean, if it's a magnet is wider, then of course it's going to increase the mass, and assuming it's the same material, it's also going to change the magnetic field. So yes, if we were to change the width, it would affect that. But we did not actually do an experiment with that. But that would change multiple different factors: the weight and also the magnetic field. So yes, that would change multiple factors, and it would affect the radius.
Okay, so can you tell me if the thickness of the left wheel and the right wheel is different?
In our experiments, they were the same.
Do you think that the difference of the radius of magnets have a direct acceleration?
In the radius of the magnets has a direct acceleration. Well, so the radius of the magnets is not what causes the acceleration. The radius of the magnets is what affects if you have the body here. That's what's going to affect the radius of the whole arc. So the difference in the radius of the magnets is not going to affect the angular acceleration as much as it affects how big of the circle is. Other than the fact that the magnet with a bigger radius will presumably have a higher magnetic field.
And the aluminum is not a ferromagnetic substance. So why would you think the device will work?
Because it's conductive, so if you can send a current through aluminum, it's a conductive metal. But, is that all?
Yeah.
Opponent, please summarize the discussion.
Okay, in the discussion part, I know that they didn't consider the resistance of the electricity in the battery, and they do consider the thickness of the left wheel and the right wheel magnet, and they do analyze the deviation between the data and data. And because I still want to know if the creases on the foil will impact the result. But unfortunately, the battery is not strong enough to accelerate the velocity to high speed. Okay.
Okay, reviewer, any questions?
Thank you, reporter and opponents. Excellent presentation. I'm the reviewer. Now I have some questions for the opponent. That you have mentioned that it will have centrifugal force, right? Centrifugal force.
Can you explain that word?
It has a circular motion,
Yes.
so there will be a centrifugal force.
Oh, yeah.
Oh,
Can I speak on this?
yes.
The centrifugal force is going to be the sliding friction is going to be, he was talking about how it's going to be moving, if it's in a circle, at any time, it's going to want to move outwards, but the centrifugal force in space is the friction.
Then the next is, in your diagram, you didn't mention which force lead the circle magnet to circle.
The magnetic force, right here, it says that magnetic, that's the,
Yes, but you can see in your video, it has a different directions, right?
what do you mean?
Just in your video, you can see that it has a different directions with the Lorentz force.
The magnetic force is always moving in the same direction, what do you mean?
Yes, maybe next page, and you have. Then thank you. Then I want to ask the opponent, what's your opinion that which force really lead the system to move?
Either what to move?
Yes, lead a circular magnet to move.
Oh, just magnetic force.
Magnetic
yes.
force. Okay, thank you.
Thank you.
Then, please turn to the page for the rolling frictions. Okay, thank you. Then I want to ask, why is the rolling friction in this expression? Because I don't know why this, because I didn't see any reference.
Okay, so the torque is going to be, proportional
So
to
where
the,
is
the derivation, okay, it's not, the derivation isn't here, but I said that basically the friction force is going to be proportional to C times A times the velocity, and
Thank
so.
you. Then what's your opinion about the rolling frictions? Is it a right, a correct sentence or not? Okay, thank you. So next will be that the right-hand rule is a simplified result for Lorentz force. Do you agree with that?
I think it's simply, it works.
Yes, so do you agree with there's no electric field in the systems?
We did not see that the electric field caused a force on the torque on the body.
So, okay, thank you. Then what's your opinion about my questions?
I think the just the magnetic field and the current will impact the force of the magnetic. So I will.
Then what's your opinion that how important the resistance of the battery is? Thank you.
2 minutes to prepare.
Sorry. So can you regress the time? Because- Sorry,
The
please,
time.
please regress the time for me.
时间
Thank you. And all of the jurors and file delegates. My name is Ricky Ho from iExplorer, Kaohsiung Senior High School. I'm the reviewer for problem number 2, circling magnet. This is the problem statement, and the phenomenon is that the different diameters of the magnet approach to each end of the cycle in the battery. And when we put the battery on the aluminum foil, then the battery will start to have a circular motion. And this is a summary and comment for the reporter. This is for the reporter. Laws applies to the right-hand rule rolling friction and the Lorentz force derive a governing equation. Changing factors are the battery voltage combination of magnets and the numbers of the batteries. But they didn't mention how do they control all the variables. For example, they just changes the number of the battery to change the battery voltage. But how do they control the variable, for example, the weight, the moment of inertia, and the frictions? So there's some problem with their experiment. Instead of our bottom magnets, calculate battery, and aluminum foil. Conclusion is that they can derive the governing equation considering the current, magnetic field, and rolling friction. Second is that the eddy current could cause error to the result. The advantage are a complete, clear structure of the presentation, good time control. But the suggestion is that they didn't consider the effect of eddy current, time resistance, centrifugal force in their model. And also, they didn't well explain what really lead the battery to move. And also, there's no completed video in their report, and didn't mention how to control those controlled variables. The summary and comment for the opponent is that he clarified many key points, and suggestion is that he should focus more on reporter's work and have some wrong opinion to the theory, and did not catch the key point of the problem statement. And the summary comment for the discussion is that the opponent actually consider the inner resistance of the battery is so important. And in my opinion, the jaw hitting and the effect of the eddy current will hit it on the battery. But in my opinion, the rise of the resistance in the battery was so small. So the decrease of the magnetic field is more important than the rise of the resistance of the battery. And what is the magnetic orientation is an SSSN. When the surface is more smooth, then the structure will start to self-rotate. So next, my question is that what is the origin of the centrifugal force in the circular motion? And the reporter say it's a sliding frictions. And in my opinion, the reporter says it's the sliding friction is the right answer, but it's not right directions because the circular motion, the centrifugal force must point at the center. So the centrifugal force is provided by the friction force. And the right-hand rule is a simplified version of the Lorentz force. Do you agree there's no electric field? So, and they also mentioned the eddy current might cause the might cause the resistance force, but in eddy current we can say that the electric field is now zero, so they cannot use the right-hand rule in their report. So which force do you think that leads the whole system to move? You can see that we can view our structure. If there is a homopolar engine, our structure is...
Yeah, hands up.
Thank you.
So for the concluding remarks of the reporter, I just want to say the internal resistance the opponent was talking about, it's already accounted for in the calculations. We showed what the internal resistance was for each of the experiments where we changed the number of batteries. And also the thickness of the magnets was kept the same for each of those when we were talking about that. And so one point that was kept coming up was how it will overcome the rolling friction. And so it's not going to slide horizontally because the centrifugal force actually is the sliding friction. So in the drawing over here, if the body is going in this direction, the centrifugal force that's making it not go in that direction is the sliding force, which is much greater than the sliding friction, which is much greater than the rolling friction. So it's not going to move out of that circular arc. And also, when I was first talking about the direction of how the body will actually move, I pointed outwards towards the audience, when instead it actually went into the board the direction of the body. And so I wanted to explain that the direction in which it will go is dependent on the direction of the battery, because if you switch the direction of the battery, that's going to switch the direction of the current, therefore switching the direction of the force and torque overall. So that's why when I pointed outwards, that was with a certain battery direction. It was the opposite battery direction causing it to go in the other direction. And also, they were saying that we didn't think about how we didn't control the parameters of weight and moment of inertia. I don't really understand that, because the weight of the body is not just going to spontaneously change, and it's not going to, the moment of inertia for the body with the battery and magnets isn't going to change during the experiment. So we don't really need to control that externally, because it's already going to be controlled. So yeah, that's what I want to say. Thank you.
Right. Okay, it's time. Do we have any questions from the juries?
Yeah, I have a question for the reporter. So the first one is, have you really observed the motion with the magnet in parallel, the magnet condition?
When they're both north-south?
Yes, yes.
No, we did not observe movement, because the sliding friction is great enough that it will not start to move.
Okay, so you haven't observed.
We were not able to observe it under any parameters, because it's going to rotate about the center, and so it would instead have to slide instead of rolling, which the sliding friction is much greater, so that we didn't observe that motion.
Okay. More any questions?
Can you comment, make some comment on the anti-current test?
Yes, because if there's if it is on inductive surface, then there must be an eddy current. So in my opinion, the resistance force for this system is not just the rolling friction, but including the eddy current, rolling friction, and the air drag force. And the eddy current not just cause the resistance force, but also the heating effect that I have mentioned.
So I talked about it very briefly. I didn't talk about it enough, but on the slide where we talked about sources of error, the diagram on the right was showing the direction of the eddy current, and we think that that was one of the reasons why the source of error was greater on slides on the bar graph on bars where the source of error was larger. We think that was because of the eddy current.
Sorry, can you repeat the question again?
Make some comment on the effect of the eddy current in this experiment.
Can you put down your legs, please?
And
I think it had a horizontal direct of affecting to the devices, thus friction is outside, and the angular velocity will cause the force inside, and the additional will cause the force outside.
More questions?
Can you help answer for the T-no values? I have answer.可以帮忙answer?
No. Okay. Any more questions from the jury? Okay, if not, let's do the breaking. so let's ready for the photo. Okay. 6, 6, 5, 8, 8, 8. For the opponent. 5, 5, 5, 5, 6, 6. For the viewer. 7, 7, 7, 8, 8, 7. Alright, finally a semi-comment. There is one back. No? Alright, then we finish this one. Okay, let's take a break.
Would like to challenge problem 7 B dynamics. We accept. Thank you.
Alright, so suppose you have prepare try to describe the name of the representative on the record.
I'm ready.
Okay, please begin.
Good afternoon, honorable jurors and guests. Today, I'm going to present problem number 7, beat dynamics. And I am Yuzhen Chuan from H105. Okay, so for the outline for my report, first we'll have an introduction of the problem, and then we'll have an observation of the phenomenon, and my theory, and then my experiment setup, and of course my experiment. And at last we will have comparison discussion and conclusion. Okay, first the introduction. A circular hoop rotates about a vertical diameter. A small bead is allowed to roll in a groove on the inside of the hoop. And we should investigate the relevant parameters affecting the dynamics of the bead. Okay, and this is our observation video. As you can see, the bead, the small bead inside the hoop, will go up on a small angle. And yes, and it's like that. Okay, next page. And we wanted to calculate the bead's motions, and we will try to use the Euler-Lagrange formula, which will try to modify to our question, and it will look something like this. Okay, next page. And we will make the Lagrange L equal to the bead's potential energy minus the kinetic energy, or L equals T minus V. And as clearly say, or could be seen, we can know that the kinetic energy T could equal to this, and the potential energy will equal to this. And by math, we can use the Lagrange equation and get a result, which will look like something like here. Okay, next page. And we can, by denoting omega c squared into G over R, and number k for omega squared over omega c squared, and defining tau equaling omega c multiplied t. By doing this, we will try to make it into a dimensionless form, so it will be easier for us to enunciate and analyze it. And so we can have something which will look like this as an effective energy here. And it will equal this. And this will be something for a number, a constant, which we could see by previous calculations. And we can separate epsilon into an effective kinetic energy in the which will look like this, and an affected potential energy, which will look like this. We'll call it the potential energy U theta for further uses. Like here, because for various reasons, we will focus on when the B is at the bottom of the hoop, and this will be the main focus of this our experiment. And from the previous equation, we can see the effective energy epsilon will equal -1, no matter what, when the bead is on the bottom. And the graph of the potential versus theta when k, the k which was defined before was between 0 and 1 here. Or when it's, in other words, when k is between 0 and, then next page. When k is between 0 and 1, in other words, means that the angular velocity is not quick enough. And by math and calculation, we can see that initially the theta is 0, which is at the bottom of the hoop, is clear enough. And the theta prod, or the angular velocity, is 0 too, which is clear enough, obvious. And however, by calculation, we can see that theta double prod is 0 as well. So the bead will stay at the bottom of the hoop, which in conclusion is that when the angular velocity is slow, the bead will not move. Okay. But when k is bigger than 1, or the angular velocity is quick enough. By enough here, I mean that it was bigger than g over the angular velocity squared is bigger than g over r, or the r being greater than g being the acceleration of gravity. And we will, by math, see that there were 3 extremum in addition to theta equals 0 and pi. and this experiment will be at omega 1 equals cosine, arc cosine the k 1 over k, and for U theta we can see this, and by this conclusion is that the theta equals pi, or when the beam is at the top of the cube, will remain the maximum of the effective potential energy. However, the zero will become a maximum, and the minimum will be the cosine point, which is, as you will see in the next page, here, this is the place where the beam will be stable and will rotate. It will reach equilibrium, and the omega 1 will increase, or the point will increase when the velocity is higher and higher. So in theory, when the angular velocity reaches in high speed, like say infinity, the beam will reach equilibrium at a 90-degree point, or theta equals pi over half of pi. Okay. So having a graph, we can consider k over 1, but by this we can see that we should consider friction. And previous page. Here you can see that the effective potential is actually higher. So you may think that the beam will oscillate between here, which is omega 2 and 0, or whatever you may think. But we need to consider friction. So even a little bit of energy loss will make the beam cannot go through the peak of theta equals 0, and by movement, the friction will use up its energy, and thus resulting in next page, as the beam will move on the circle of radius a sine omega. Okay, so the possible parameters are hoop radius, weight, and whatever. But in this experiment, we will focus on the angular velocity and the omega 1. Okay. And this is a setup. It will look like this. Oh, okay. And I don't think I need to explain everything, but in conclusion, it's just like when the hoop spins, it will pass the photoelectric timer, and we can calculate the time, which when it spins half a circle. And by doing this, we can calculate its angular velocity, and by using tracker, we can calculate the height, which by the height we can like see the angle. Okay. And this is our experiment of the height of the beam versus the t squared. And by math, and which I have shown or maybe told in previous pages, we can see that the graph will look like this, and it has a meaning. So this is like why I would do it like this, not just measure the angle. It's because that by calculation we can see that cosine 1 over k, our cosine 1 over k equals the angle, right? So when the cosine of the angle will equal 1 over k, but remembering the definition of k, we can see that easily that there will be a constant and some number. So, and okay, I'll just go to a conclusion. It's okay, next page. Okay, this is another experiment. So we tested when t squared is over 0.1, and from the same conclusion as before, the theory suggests that the beam will not move, and it does not. Okay, so this is how we calculated. So we should expect the dots have a linear relation, and while slope being minus g over pi squared, and the intercept of the x-axis or the y-axis is the radius of the hoop, which was close enough to our experimental result. Okay, so by comparing it, it will fit in quite well. For the hoop radius is like 0.1, and it just fits well. But there is still some little difference that you might see. in our result and our theory. We have like some deviations. We do not like knew it like very specifically, and we believe that maybe the measuring of height could be altered by, say, camera angles or maybe different just regular deviation by human eye. And the rotator cannot have a beautiful spinning speed, which may lead to a little difference between theoretical and experimental result of our time. Okay? And here is my conclusion. The bead will go up the hoop when the hoop spins fast enough, or in other words, the omega squared exceeds G over R. And when the hoop spins faster, the bead will go higher, which was seen in the previous graph. And our experiment and theory, experiment result and theory, both suggest that T squared and H have a linear relationship, while the slope being the negative G over pi squared, I think, a constant. And it was near 1. And from theory, we can see this conclusion, which is the boundary of the bead's motion. And when k is smaller than 1, it's somewhere around omega smaller than pi over the square root of 0.1, or precisely omega is smaller than the square root of G over R, which I have just stated before. Okay? So, thank you for listening.
Mona, please ask questions.
Hi, ladies and gentlemen. Hi, Jerry. My name is Henry Xu from Thing I Explore. First of all, thanks reporters hard working towards the presentation and the experiment as a whole. A wonderful presentation. So, first of all, I would like to ask a question regarding to the experiment. Can you show your presentation?
Okay.
This one? Yeah, in the video. Can you play the video?
Oh, the video. Okay. Oh, okay. Here.
So how can you get the height throughout this video? I'm quite confused. Since
You mean get? Oh, yeah. Because we can just take like frames of when it's faced here, like when go to a center page.
So where exactly?
We could get a page like something like that, and by the bead is yellow and the hoop is red, which we can actually by. Oh, I do this just to let you see for the electric timer. By real experiment, we get in a closer view. So like the video, we can see the bead quite clearly. And when we see the face, which faces us, and at the same time, the photoelectric timer reaches like the time, we can see the bead angle.
Yeah, I understand. Previously, you talked about there's a camera angle difference or error created because of the setup. How can you correct that problem?
I may think like we could try to like make the camera angle like to tilt more high, or maybe try to shot it like straight to the center of the circle.
So basically, you're talking about using different camera angle to adjust camera angle problems, right?
I'm saying that I think that deviation may be caused by camera angles. There was just one of my.
So can you tell me again where exactly is the bead in this picture?
Here, it's this.
Oh, right. Thank you. Understand.
Mona, you have to show it where.
The reason that you use cushion motion is because you want non-static dynamic result. There's no dynamic result, only static result. Why do you use equation motion if there is no dynamic result and only static result? And how can we improvise our static? select results which are, let's say, simulations or any more notation you can compare with your actual experiment data. So how can if you have a theoretical model, how can you if have a practical model, how can you compare the model with your experimental conclusion? 记得提醒我讲动态的那个结果。
Hi, juries, ladies and gentlemen. My name is Henry Su from Think Explore. Today, I'm going to be the opponent of problem 7D dynamics. So, first of all, let's take a quick look at the problem statement. The problem statement basically means with a circular hoop and a bead put inside a grove with a circular hoop, the bead can goes up to a certain point and investigate that dynamic motion. So summary and comment of the reporter's report. First, he started his report with talking about a Euler-Lagrange equation and equation of motion. The setup he contained are a circular hoop, bead, and a motor. And the parameters he conducted are different angular velocity, single hoop radius, and different bead weight. However, the experiment he only did is finding the relationship between t squared and h. And the result he got is that the higher the angular velocity, the higher the stable point is. And when angular velocity is not big enough, it will stay at the bottom. And there's a linear relationship between t squared and h. And some pros and cons, first of all, clear explanation of their formula, great voice, and speaking speed. Some suggestion, it did not include drag force in their equation of motion, and more experiment video and data are suggested to put on the presentation. And there could be more improvements to the setup, like the camera angle, etc. So here my discussion summary. Regarding to the theory, first question, why do you use equation of motion if the results are a static result? Since the reason that we use Euler-Lagrange equation and equation of motion is because according to the problem statement, we want to have a dynamic result. However, in the reporter's report, he only talked about the h and the relationship between t. It should be a static result. And what caused the b to go up from its original status? Since the reporter talked about the b should be usually on the bottom of the hoop. So what force or what thing causes the b to go up from its stable points? And if you consider drag in your experiment, what difference will it make to your equation of motion? And what do you think the acceleration of the hoop affect the motion of the b? Since the reporter didn't talk about whether he done his experiment in a fixed rotational speed. So if there's an angular acceleration for the b or for the hoop, does that affect the experiment? And how do you know the beta is in unstable equilibrium points or a stable equilibrium points? Since there are two types of equilibrium points in the physics world, and what kind of equilibrium point is it in your final result? And regarding to the setup, what kind of drag force do you think there is in a setup? Like I said, if you consider a drag force, what kind of drag force does the reporter think we should include? And regarding to the experiment, what do you think the alpha angle, which is your Typt angle, I hear by alpha, sorry, affect your experiment? And how do you get the theta angle of your bead? Since we want to know that stable point, so if how can a reporter calculate that theta, or even calculate the h of his report, since there's a camera angle error? And if you have a theoretical model, if today reporters build a theoretical model and physics model, how would you compare your actual data compared to that theoretical model, and how percentage of error do you think there might exist? In the conclusion, are there any other motions that are observed, such as the oscillation about the equilibrium point, and or any sort of damping effect on the motion of the bead? Thank you. That's my opponent's stage.
For the discussion.
Okay. Again, thank you for your hard working towards the presentation. I would like to start off with the problem regarding to the experiment. Like you said, there's definitely a camera error occur in your experiment, correct?
No, I mean, there could be. I didn't say definitely.
How is that it could be? Let me show you a demo, for instance. If you today put your finger in front of your eyes, right? And you move your finger horizontally,
Yes.
there shouldn't be any y-axis variation, right?
Yes. So.
Yeah, so today, if you, however, if your eyes are the camera, you put your hand down here, and you move the bead, you move your hand forward, there should be a y-axis y-axis variation, right?
Yep.
So that's the same effect as your camera. So how do you fix that problem?
Oh, I only mean from the discussion that I only say that the error might come from the camera angle, which, as you say, there would be a difference. But can I see my my experimental results?
So how many error percentage is that?
Oh, that could be my fault that the error percent, I do not calculate the exact error percentage.
Okay.
But I should say that my experimental results were quite near my theory, and I think I just only say that to discuss that I think maybe a little bit error, like because it's an average of like 30 times of experiment. So I could just say that like sometimes of error could be caused by camera angles or etc.
So
it was
just to clarify, how do you get the error bar of your experiment?
I just used
Excel and include standard deviation, right?
yeah.
So you create that error bar. Okay, understand. So you think your device has pretty accurate results? Yes.
What do you mean by pretty accurate?
As accurate result. Yeah. Do you think your device has an accurate results?
I think it's accurate enough for it to fit in the theory.
Okay, understand. So let's move on to a more theoretical problem. So,
Okay.
Since the problem statement wants you to talk about the dynamic of the bead, and
Yes.
the bead, like you said, are usually at the bottom of the hoop, right?
Yeah, I've said that due to experimental tactic, I've tried to close up the hoop
Yes.
to make sure that there were no environmental.
Sorry, can I finish my question?
Okay.
Sorry. So if your bead is in the bottom of your hoop, then under what circumstance will the bead go up?
As I've said, when the angular velocity is quick enough, it will go up. I'm not sure if you're asking me to explain why it will go up, or asking in what circumstances it will go up.
So you're not sure.
I'm not sure of your question. Can you say your question again?
So since, like you said, if your experimental setup is so accurate and so perfect, there shouldn't be any, let's say, perturbation occur in your experiment, which is, let's say, motor vibration, hoop displacement, stuff like that. And theoretically, if there is no perturbation for the bead to leave its unstable equilibrium, at the bottom of the bead. The bead will never leave its unstable equilibrium point. So what perturbation do you think causes the bead to go up?
Oh, wait a second. Can you change to the potential graph, the second potential graph?
Yes.
The other one. Yeah, this one. You can see that by our theory,
Yeah.
our affected potential energy, which might be not that straight, when the bead is at, when the theta equals 0, or when the bead is at the bottom here, in this graph,
Yes.
the potential energy is actually higher than the place where it's stayed at the higher place, which is
Yes.
omega 1.
Understood.
So, as I've said, when the hoop rotates and has an angular velocity, we could see that when the bead will not stay at the bottom because it has a higher energy there. So, yeah, you can think that on the bottom of the hoop is actually higher than the higher place on the hoop.
Oh, so you're suggesting if the perturbation is not important, since if you're putting on the bottom of the hoop there, the potential energy is definitely higher. Right?
The affected potential energy is definitely higher.
Okay,
Yes.
affected. Okay, understand. So, can you show your equation of motion again?
Equation. Oh, okay. Change to that page. Do you mean this one? Oh, wait.
Yeah.
Yeah, this one.
Lagrange.
Yeah.
Okay, so,
Okay.
like I said, in the physical world, or our understanding, in my humble understanding, the reason that we use equation of motion is to understand the dynamic effect. Let's say the theta acceleration against the theta direction relationships, etc. So if it is a function talking about a dynamic result, why is your research is talking about a static result? Let's say an h against a velocity. So, or if today, if you want to get a simulation regarding the dynamic result, how will you improvise?
Dynamic result?
Yes.
Oh, I think I've seen that the question makes us to see the dynamics of the bead, which seems like in different points of which alters the bead's dynamics. But in my experiment, which I may say that I have like not enough tactic, so I could only make the bead stay at the bottom. So in this, the dynamics, there are only two kinds of dynamics, which is the bead does not move or the bead moves as a circular. But if you want to know that if I have the tactic to put the bead on a higher place, when the hoop has an angular velocity, the bead will oscillate between the two angles, or when it's quick, when the bead is put at the highest point, it will spin round and round on the bead.
Okay, so understand. So in my previous understanding, I mentioned that have you ever observed a slight, let's say, tumbling phase in the bead motion when the bead goes up?
What do you mean tumbling motion?
So the bead in my understanding, or in the physics world, there should be the bead should go up to a very high place, which is above its supposed stable equilibrium points, and go back down again. So you should have a decay sort of effect. Have you ever observed that?
You mean considering the friction, so it will have a decaying effect, like oscillating back and forth until it stops at a point.
Yeah, sorry. Let me draw.
Oh, okay.
It's on the board. So, like I said, since the problem statement wants you to talk about the dynamic results,
yes.
So it should be a relationship between, let's say, the theta, or you can say x. It doesn't matter.
Yeah. Okay.
In that case, in that matter, the theta relationship against time. So if today you have the same angular velocity.
Yeah. Okay.
So how will you draw your theta angle against time in this instance?
The theta angle against time. You mean when the bead's down at the bottom?
So yeah.
And you mean I need to say that from experimental results, it will look like something like maybe those of them that it will just at some point. But this is due to my ring having a high friction. So before it reaches the equilibrium point, which here is omega 1, before it reaches over here, its energy will all used by friction. So if I I have the priority to change it into
Yes.
a material of
Yes.
very small friction. It might not look like this, and as you have suggested, it will go up and down and up and
Oh, yeah, I understand. So, so if today like your Euler-Lagrange equation wrote, is this S or
I think on theta, oh yeah, it's the same.
Yeah.
Sorry. Theta and angle is the same, I think.
Yeah.
Yeah.
So if there's a, like you said, and drag force created, will this still be equal to 0?
Oh no, I mean, we could add we can consider the friction after the when we see the result. I mean, this is the like theoretical result which we do not, and it will like oscillate like infinity.
Okay. So so that's a last short question. So can you explain? So if you have the time and the setup,
Yeah.
will you consider that drag force?
Yeah, I will consider it. Like I will see the coefficient of the friction, and I will see like in how many times it will go back and forth.
Okay, I understand. Thank you.
Thank you.
Opponent, please summarize your discussion.
Okay. First of all, we talked about the setup of the reporter's report. In my opinion, he could definitely improve his setup since to the camera angle, like I demonstrated with my hand and my eyes as a camera, there will definitely be that y-axis deviation. So some adjustment can be done definitely to improve his accuracy. And we also talked about the hypothesis that whether if it's on the bottom of the hoop or how does the bead goes up, like the reporter says, when the bead is in the bottom of the hoop, it has higher potential energy. And we also talked about, are there any more interesting dynamics you can find throughout the theta against time power? Like the reporter says, since his setup has a very high friction, if today you have a lower friction, maybe he will consider it, and if he has the time, he will consider putting a new drag force in the Euler-Lagrange and draw a new theta against time plot. Thank you, Jerry.
Review of the next questions.
Alright, so the first question is to the reporter.
Oh, sorry.
Okay, it's no problem. Go to time 15, please. Okay, so you mentioned that it is t squared versus h. Can you explain why? You talked
okay.
about how it's the graph of time versus height, but why is it t squared over there?
Here. I have the calculation here. So this is, I've said in the previous page, but I've put here for convenience for all of you to see. And from the previous equation, we can get this, which was
Okay, thank you. So,
yeah.
and please go to slide 6.
Okay.
6. Okay, so just to clarify, you talked about how the bead's potential energy is, you have to talk about the Lagrangian is potential energy minus its kinetic energy, right?
Yes.
Okay, so, but in your V equals to mg part, that part, that is actually the potential energy portion because it's mass times gravity, that portion.
Yeah, I think it's a potential energy.
Yeah, but why is that subtracted over there, but then you're saying that it's potential energy minus the kinetic energy over there? Please explain how you theorize this.
Wait, can you state your question again about what like negative thing you say?
Sorry, can I clarify for him?
Sure.
So basically, Euler-Lagrange equation will never be changed. It will be always the kinetic energy minus potential energy. So the reporter and I didn't quite understand and review your question. So basically, according to our understanding of physics, the equation of motion result is correct.
Okay,
Thank you.
and question is to you both. Have you considered the friction of the contact friction at the original stationary critical point?
You mean the contact friction of the original stable point?
Yes.
I did not consider, but I think it will not affect too much.
Can I answer? So through your Euler-Lagrange equation, his particle model suggests there's no drag equation. So regardless of any drag force you consider, if you want to put a drag force inside your Euler-Lagrange equation, you have to have adequate function. So I don't think it is necessary to put that drag force because it's more complicated than as you expected.
Okay, and the question is to you both. how do you suppose like changing perhaps the material of the bead, the mass of the bead, and maybe perhaps also the radius of bead would affect the rate of which, or the theta, the final equilibrium theta?
Oh, you mean changing the radius, the mass, and
Yeah, or maybe even the material. How do
Oh.
you think that would change it?
the material will change the fraction, of course. As I've stated before, it was just like changing the Hoops material. It would be like the
So
same.
you think that's a potential new experimental process you can go through in your future work?
I think it's just changing the material of the bead. Same as
Time stop.
Okay.
So, we will have 2 minutes to spare.
Alright, so the problem statement is already stated, so I don't think I need to repeat that, but then the main focus is also here, so it's basically talking about how the bead moves the way it does, and as well as the prevalent parameters that affect this phenomenon as well. Yeah, okay, so for the reporter's performance, he had a decent mathematical explanation of how the theory occurs, and he also considered some aspects of the friction, and he had a fairly concise and clear explanation of the phenomenon. However, he had a very, very brief explanation of how he set up the experimentation. Right, so that the axis was off, and then he had a tilted he had a tilted hoop, which caused more errors as well. At the same time, he also did not show the equilibrium position exactly in a video or something like that, and there was no physical application of the theoretical model. Okay. Yeah. Okay. And then as for the opponent's performance, he well summarized everything. He had clear and concise sentences. However, he had a bunch of questions, but then he didn't really properly explain a lot of the points that he tried to say. Alright, so one of the discussions they had was about setup, and basically the opponent said it did not clearly explain the experiment of the setup, that the bead was actually moves up. And I actually agree with the opponent in this case, because the experiment results are actually kind of flawed because it's tilted, it's not off the axis, and all that. There's also the initial condition of the experiment, basically about the camera angle, how it's set up, all the experimentation errors. There's also the view part, which talked about how there is the effective potential energy that causes the bead to go up. I actually disagree with that statement because it's actually depending on the bifurcation, which means the direction of the spin, of the angular spin, and that affects which direction the bead goes. And it is actually the kinetic energy that makes the bead go up, not the kinetic energy. Okay, so they also discuss drag force, angular velocity, all that kind of stuff. Yeah. Alright, so but for the points missed, one of the main different types of parameters in this was actually the material of the bead itself, or other relevant parameters would be like mass of the bead and then the radius of the bead. At the same time, they didn't really talk about the actual angle from the vertical direction of the slide. Okay, from the slide calculation, I think it was slide 6 or something. Yeah. Alright, so the mass of the bead, radius, yeah. And then as for the friction, the reporting side and also the opposition side, they didn't really talk about the oscillating friction and the equilibrium stationary friction from the initial start. So that was a point missed. And at the same time, they didn't really, for the reporting side, they didn't really correct how the tilting matters in this case, and then they need to correct it in their future experiments. I think I talked about bifurcation. It's basically if you change the sign of the angular velocity, the direction of the bead's angle also matters as well. So it depends on the angle. And at the same time, just to clarify for the reporting side, they talked about how it was the potential energy minus the kinetic energy, but it's actually kinetic energy minus the potential energy. Yeah, thank you.
Alright, so
Okay. So for my concluding points, and these are the questions we've been discussing with the opponent. And as the question about the camera, we can consider it in an experiment, and we can do it by closing camera near to the hoop. And the acceleration of the data, we added an error bar by adding a standard deviation, and we compare the experiment result with the theory, and finding close to our expects. And about the question about the Lagrange equation is used to describe motion, and my experience is mostly static. My experience does state that it was important that it is good enough to state our motion, but it was just a fact that our motion is mostly static. So I will not have like too much compliment on this. Okay, and so to conclude my concluding remarks, we have a clear relation between our parameters and have calculated the standard deviation. We agree that there might be the impact on friction and drag force which our opponent and we will have stayed and in between the whole experience. But according to our main equation, we think the best method is to improve our result and just add more parameters to our experiment by measuring and not calculating, because our equation fits our needs. And I think to add more parameters, we should not add to make it more complicated, make our equation more complicated, but we should measure it. Okay, thank you.
alright. Okay, so let's the time for the question from the jury. I have questions for the reporter first. Are you sure your rotating axis is passing through the center of your loop? Can you show your video? I don't think you.
I see. Wait for a second. Sorry, there is a little bit. Okay. Wait. Wait. Sorry. Please wait for a second. Our PPT is not working properly. Okay, now it is. Okay. Go to the page of my demonstration. You mean the rotation axis is not, does not go through the center of the hoop.
Yeah.
Because I must say this is my fault, but I do not have it like to the most perpendicular or the most straight mode, but I think that this is clear enough to give a demonstration of the phenomenon. And in my calculations or in my experiment, I does fix this problem.
Can I answer for you?
All right, just question for the reporter. I have now the questions, because you conclude in the conclusion, drag force need to be considered, and also the opponent mentioned this. So is drag force important?
I'm not sure if it's important or not, but according to the opponent, he thinks that I might need to like consider the drag force, and I say that we can consider it if we have better equipment, as my opponent has said. If I does have better equipment, considering the drag force, even if it does not affect much, would make it more precise.
Yeah, just concise answer. Yeah, that's
Oh,
fine.
okay. I was just giving a short answer.
Yeah.
Is that I think we can improve it by our experiment.
Yeah, for the opponent, why the drag force instead of a friction force is important?
If there's no drag force considered, the motion will be totally different. According to simulation and the Lagrange equation of motion, the effect without drag force will be like this. A sort of the bead doing a simple harmonic motion, sort of a simple harmonic motion inside the bead. And it's more complex than that. But
my question is, why is drag force instead of friction?
Very good question. In my experience, that since if you the way we add a drag force is through a negative EV, right? And if it's a friction force is a constant, it's very hard for us to put it inside the equation of motion. That's my answer. Thank you.
Okay, that's your question. Other question?
And then,
okay. Well, since there's no further questions, so let's just go to the grading. All right, ready? Okay, for the reporter, please show your way. 5, 5, 5, 6, 6, 7. Okay. For the opponent, please show your way. Uh, 7, 8, 6, 7, 7, 8. For the reviewer, show the way. 7, 6, 6, 5, 6, 8. Right? Okay. Any comment? Do you want to make? The last one. Any comment? No? Maybe everyone's okay. With no comments, just let's finish here. And thank you for your all participations.
Thank you, Chairman.